So this is now the final question for AQA's AS Physics. This is the June 2009 paper. Okay. What we've got on the board here is sorry, let me just get to the correct page here. Yeah, sorry, just making sure it was G9. I thought it was going crazy. Okay, so we've got a diffraction grating here. Now, this question I think is stupidly easy. Well, it's not stupidly easy. It's easier than most diffraction grating questions that you might get in the exam. Okay, so what we've got here is this narrow beam of monochromatic light, which means it's of a single wavelength. Okay, so it's very direct, probably come from a laser beam. Okay, it goes through diffraction grating and comes out as this split up light. Okay, now it's not shown as it in terms of orders or what. It's not asked anything about that yet. In fact, it's even gone to the trouble of telling us what the grating spacing is. And I've labelled that because you might not be familiar in terms of, well, what does that relate to the equation? Okay, well, it's represented by the little d in the equation. Okay. Now, they may ask you to calculate that, and if they did, what the formula would be is n equals 1 over d. In other words, the number of lines per metre is equal to 1 over the one over the grating spacing, okay, which is said represented by little d. But that's another little equation, if you didn't already know that, to work out d, if they don't give it you. But as I said, they generally don't. But in this case they have, so you obviously don't need to do that. Right, and there's no point working out that big N because there's nothing you can do with it, okay? That's just purely to help you work out D. Anyway, the 7A part 1, calculate the angle of diffraction of the second order diffraction beam. So this is, as I said, one of the English questions you'll get. Okay, so it's a second order beam, okay? So the big N is equal to T. Sorry, not big N, sorry, small N. I'm going off. It's the second order, okay? And what it wants us to work out is calculate the angle of diffraction of the second order beam. Does it tell us the wavelength? Oh yeah, sorry, it tells us the wavelength as well. It tells us the wavelength is 590 nanometers. Now remember, nano, it's milli, micro, nano, in terms of it goes up in -3s if you convert it, okay? Or 3s, or whatever which way you convert it, doesn't matter. Okay, so 590 nanometers is 590 times 10 to the -9 meters, okay? So it's 590 times 10 to the -9, and obviously if you put that in your calculator will put it into standard form, but it means the same thing. Alright, so that's lambda. We've got our diffraction spacing here, so we just use the simple formula n lambda is equal to d sine theta. Okay, and it's just a case of rearranging. So it's 2 times this whole wavelength thing, which is 590 times 10 to the -9. As I said, if you put it on your calculator, would round it, so it was in standard form, and it would probably do 10 to the -7, I think, but doesn't matter, you can leave it as that, is equal to D, which is obviously the 1.67 times 10 to the -6 meters, times the sine of the angle of diffraction, sine theta. Okay, and it's just rearranging and inverse sine or arc sine or whatever you want to, how you say it, to get theta. Okay, so I'm just going to go straight to it. So theta is equal to the sine inverse of 2 times 590 times 10 to the -9, and that's all over, well, in the sine bit, the 1.67 times 10 to the -6. Okay. And you shove that all in your calculator and you get the angle for theta. Okay, so I'm just going to do it on my calculator. So it wants it in degrees, okay, just making sure. So the inverse sine of 2 times 590 times 10 to the -9. Okay, and that's over, so 1.67 times 10 to the -6. Okay, and we sort that out, okay, shove it in your calculator, you get 44.957, okay, in other words, 45 degrees, okay. And the reason I've done that is technically to 3 significant figures, because this is to 3, so you want to do that to 3 as well. but it's up to you. Okay, and it's not going to penalise you for that. 7A part 2. Show that no beams occur higher than the second order can be observed from this wavelength. So what you do, now this is, well, I said this question was the easiest diffraction question you'll ever get, and you may go, ah, well, this question proves you wrong, you stupid fool. Well, I argue against that, because all it's asking us to do is manipulate this equation to show that we can't have a third order beam. So there's a couple of ways of going about this. Okay, as I said, they've done the way in the mark scheme, which I'll go through in a minute. But I just want to highlight another possible way of doing it. Now, it says you can't have a beam which is greater than 2. Now, if you put a number in, say, 2.1 or 2.2, and I'll go all the way up to the actual value that you would get, I think it's 2.83. But you can't have 2.83 order of a beam. It doesn't make sense. That isn't a beam. It's either the second or the third. It's not statistics or science, sorry, it's not maths where you can have 2.5, 2.7. What is it? It's physics as well. But what I'm trying to get across is it's either the second or the third beam. You can't have halfway between one beam and another, because that is a beam on its own. Okay. So what you could do is you say, right, you do the sub in 2. Okay, for this, which quite clearly works, we've shown that you get an angle for that. And if you put in 3. Well, obviously you won't get any. You won't get a third beam, and obviously you can't have a -2 beam either, because that doesn't make sense. You can't have -2 beam. Okay, it doesn't make sense. There might be a -2 beam if you're going from right to left or left to right, but it'd just be the second beam. -2 doesn't make any difference. Okay, so what I'm trying to say is we won't have any greater than 2. So obviously the third beam wouldn't work. So you could put n to be 3, therefore, and obviously prove that doesn't work. Say therefore there's no beam higher than 2. But what they want you to do is they want to show that you can't have a beam higher than 2. Okay. So for this wavelength, so we've got to keep this wavelength here. So we know the wavelength is going to stay the same. This is now as you were doing it if you were doing it in terms of how it's done it on the mark scheme. Okay. So we said the wavelength is 590 times 10 to the -9 in meters. So you need to make sure it's in meters. N, well, we've got to work that out. Okay. We know, well, so the grating spacing won't change, so little d is 1.67 times 10 to the -6 meters. Okay. And we don't know the order of diffraction. Sorry, we don't know the angle of diffraction, because we're going to prove that it can't be done. Okay. Now you may be going, well, we've got 2 unknowns there, so we need 2 equations, and we can only come up with one equation using the idea that n lambda is equal to d sine theta. Well, I argue against that. What's the maximum value of sine theta? You go, oh well, the sine theta is obviously related to the sine curve, which does that. Okay, and the maximum value of sine is the maximum value of this curve. Well, yes, that is correct. And you go, oh well, we don't know that because it could be stretched by any amount. Okay, obviously depending on what the diffraction is. And you go, well, therefore it's 1.67 times 10 to the -6. Well, that's wrong, because the height of this sine curve, yes, it may be stretched, but the maximum value of sine will be 1. Okay, so the maximum value of sine theta is 1. This is assuming you've got a 90-degree angle. Okay, so your theta's 90. We wouldn't assume that. Okay, but the maximum value of sine theta, doesn't matter what it is, the maximum value will be 1. Okay, so my value of sine theta is 1. So we can replace this sine theta with 1, or in other words, just kind of ignore it. Okay, so therefore the maximum value of theta occurs when n times lambda is equal to d, and we know n, we don't know n, we know lambda, we know d. Okay, so we just sub in what we know. So therefore n, the maximum value of n is equal to d over lambda. Okay. So therefore the diffraction grating is obviously 1.67 times 10 to the -6 over lambda, which is 590 times 10 to the -9 meters, and when you sub that in your calculator you get about 2.83. In other words, you go, well, we could round that up. Well, you can't just invent the next little bit of the You can't just invent the next little beam that doesn't exist, because that's the maximum you can get, the 2.83 beam. Which you go, well, it says it's greater than 2 and you round it up. Well, that's the key mistake that some people make with this question. They rounded it up, and you can't just invent a beam that doesn't exist. Okay, so you have to think logically. Now, in the exam, bear in mind, you might just round it up and go, well, actually, that's incorrect. Well, it's told you that you can't have a beam greater than 2. So if you round it up and say, well, you can, you have to think, well, is that right? Just you have to think about the context of the question, okay? Alright? So hopefully that kind of explains that. How much have we got left? I probably don't have the time. Great. It doesn't matter. I will still continue with this. I'm just going to take a quick pause while I plug my camera in. I'll be back in a second. Sorry, I just had to have a stab sorting out, so hopefully it will still work. Now, this next little bit of the question, again, it's just a rearrangement of the standard m lambda is equal to d sine theta equation, okay? So we're told there's a little paragraph here that says the light source is replaced by a monochromatic light source, so again, just means of a single wavelength, but we don't know, it says it's an unknown wavelength, and a narrow beam of light is, from this light source is directed normally at the grating, okay? The measurement of the angle of diffraction, the second order beam, so say little n equals 2 again, gives a value of 42.1 degrees. So label it out as, sorry about the numbers there, like you have done all the other questions so far. So you label what you know. Okay, so we know it's the second order, and we know this gives an angle of 42.1 degrees. Okay, show myself. Okay, and it's going to have the same diffractions, grating spacing, because it's going to do the same diffraction grating. Okay, so little d is still going to equal 1.67 times 10 to the minus 6 meters, and we want to work out lambda. Okay, so it's just a rearrangement of n lambda is equal to d sine theta in order to get lambda. So quite clearly the wavelength, therefore, rearrange this, just divide n by divide both sides by n, so we get lambda is equal to d sine theta over lambda. Okay, show all you're working obviously. Okay, so see, d is this 1.67 times 10 to the minus 6 meters times the sine of 42.1 degrees. Okay, and that's all over n, which is 2. Okay, so just showing the numbers now into your calculator. Okay, so the wavelength is equal, I'm going to get my calculator correct, is 1.67 times 10 to the minus 6 times the sine of 42.1 over 2, because that is the order, okay? And you'll get the wavelength to be 5.598 times 10 to the minus 7, or in other words, to cut it short, 5.6 times 10 to the minus 7 meters, remember, giving it in, that's the wavelength, okay? I suppose, well, yeah, I suppose that's acceptable. It doesn't say it's a certain amount of significant figures, so we assume that to be appropriate. Okay, so as I said, it's 5.7 times 5.6 times 10 to the minus 7 meters is the wavelength. Okay, so very easy question 7. Really, all it is manipulating n lambda is equal to d sine theta. You didn't even have to use that other equation, which is the number of lines per meter is equal to 1 over the grating spacing, makes sense, okay, which I said is denoted by a little d in the equation. So the only difficult part of that question was realising what d was, okay, that was little d, but if they don't give you that, they will say that it has 300 lines per millimetre, which obviously you need to convert to metres, okay, so there's 10 millimetres in a centimetre, and obviously therefore there's 100 centimetres in a metre, so you just times it up, okay. But as I said, they gave you the grating spacing in this equation, so I think question 7 was very, very easy, especially for question 7. I mean, to be honest, I thought it was a fairly standard paper. There was nothing too tricky in that paper at all, I don't think. I mean, it is A-level, so you can have a few difficult questions in there. But anyway, that's the end of the paper. So thanks for watching. Hopefully it wasn't too difficult. But as I said, if you've got any questions on the paper, or if you want me to email you an exam walkthrough for this paper, where essentially it's just a written version of what I'm saying, it might give you a bit more heads up, and I'm not wailing my arms around. Obviously, I can't do that in words. I might put a few hands wailing around on the paper, but it might give a bit of extra guidance, and anything I might have missed, that will definitely be on the walkthrough. Okay, but if you get all that, it's perfectly fine. It's a very easy question to be able to understand, and fairly standard paper, so I think the grade boundaries might have been a little bit higher on this paper, but as you can see, that was for obvious reasons. Okay, well, thanks for watching. We'll see you in the next paper or video, or whatever you decide to watch.